Section 7.1. Today we're going to take a look at an introduction to finite decimals. First, vocab a little bit. The word decimal actually comes from the Latin word meaning 10. Right, that's that DEC at the beginning. A little bit of language that you're familiar with, but just as a reminder, I'm going to put some placeholders here, and then there's going to be a decimal point, and then I'm going to put a few more placeholders. All right, so I think I've got 6 to the right and 2 to the left. So when we're working with decimals, each of our place values has a value name. And so we're going to just start on the far left, and this is the tens place. And then you have the ones place, or sometimes called the units place. Depends. As we move to the other side of the decimal, the first one is actually called the tenths place. So anytime you see that THS, you're talking about values that are on the right-hand side of a decimal. And then we work our way up from there. So we have the tenths, and then we have the hundredths. And then there's the thousandths. Do you guys know what comes after the thousandths? Yeah, it's 10 thousandths. Then what? Yep, 100 thousandths. I'm going to shift this up because I'm running out of space. Oh, I guess I lost part of my word. Let's shift that too. Okay, yep, 100 thousandths, you're right. Do you know what the next one is? Yeah, you're right, it's millionths. And I'm not going to write any more out, but if you needed to go one more, do you know what it would be? 10 millionths, and then 100 millionths, and then we go to billionths and so forth. 10 millionths, I think, is the smallest number that we see decimal notation for in any of our homeworks or anything like that. But yeah, they work their way on either side of the decimal point in that direction. We're focusing mostly, of course, on the right-hand side because we're working with decimals now. Whereas back in the earlier chapters of this book, chapter 3 and so forth, we're working with the left-hand side before the decimal point. So the first thing we're actually going to do is we're going to take a decimal expression and we're going to write it out in words. And in particular, the decimal point itself gets written as the word and. So you can kind of break it into two pieces. We're going to look at the number beforehand. What is that number? 32. So that's how we're going to start. 32 actually has a decimal between the 30 and the 2. Not a decimal, hyphen. It's like, that's not the right word. A hyphen between the 30 and the 2. And then we have the word and to represent our decimal point. What comes after this is first written as though it were not, as though it were a whole number. 4236. If I just gave you the number 4236, how would you say that number? Exactly, 4,236. That's what we're going to write next, okay? So 4,200. 36. And then we have to indicate where it ends. Where does that 36, or the 6 in particular, have its final resting place? In particular, if you were looking at this location and thinking about it like we wrote out all of our words, what place value is the 6 in? 10 thousandths. So then we would write 10 thousandths. Does that make sense to everyone? So you're writing the number on either side as though you were writing a whole number. The only difference when you're writing the values on the right-hand side is identifying what place value you end at. Okay, we're going to do it the other direction now. We're going to take a word. or phrase, and we're going to write it in the symbols, the numbers instead. It says write 536 and 76 thousandths as a numeral. So once we get that and, that's our decimal point. So the first piece right here says 536. What does that look like? 536 and then a decimal. And then we have 76 thousandths. So as we're looking at it from this perspective, we need to figure out how many values we need on the right-hand side. Because just because 76 is a two-digit number doesn't mean we only need two digits necessarily. Where do we have to end? What place value do we have to end in? The third one. So the 76 has to end in the third decimal place over, which means I don't need that last mark. And the 76 will be here, which means what goes in the place that I didn't put anything? It's a 0. So it's one of those things that can catch us off guard if we're not paying close attention, because 76 looks like a two-digit number. We just need to make sure the two-digit number is resting in the right location. Is that okay so far? Okay. So we're going to shift gears a little bit to talk about some visuals. We're going to talk about base 10 expanded form, and I do this a little bit differently than your book. So this is like your warning. I don't want you to use the notation of the book. I want you to do it this way. And I'll explain why so that you can get some sense of why I'm doing it. So for starters, we're just going to write the place values that we just had on the previous slide. So we had, let's see here, without all their words, just the symbols. I don't think I need all of them, but we'll catch most of them. Probably 3 decimals is enough on the right, so we'll go with that. And I'm going to go with one more on the left as well, just for, okay. At this point, I really think just drawing it was probably the best way to go. All right. I want to write, instead of the words out, like we did before, I want to write a numerical value out. In other words, I want this to be written as the number 100, because it's the hundreds place. I'm going to write this as the number 10, because it's the tens place. And this is the number 1, because it's the ones or the units place. So hopefully that's all right. Everybody good with that? On the other side, I want to write these in that fractional form that we have seen and thought about before back with chapter 6. This is the tenths place. As a fraction, I can write that as 1 over 10. The hundredths place, so I can write that as 1 over 100. And the thousandths place, which is 1 over 1,000. So notice this disclaimer on the bottom of the page. What your book does is it likes to use exponents here. So what they would have written, and if you see it, they'll see that they'll say 10 squared, 10 to the first, 10 to the 0. This will say 10 to the negative 1, 10 to the negative 2, and 10 to the negative 3. That's what it will say, okay? I don't want us to use that notation, and the reason I don't is because I don't think it lends itself very well to conceptual understanding of what you have. I think when you write it in that fractional form instead of this notation with exponents that are negative, you lose some of the grasp of what you're finding and what you're actually getting a value of. So we're going to, as we write our base 10 expanded notation, not use anything that's in red here. All right, so this is going to be a no-no, even though I know that as you look in the back of the book, your book's going to do it. I really want you to write it in the base 10 notation with our fractional expressions, okay? So as we see an example, you'll see what I mean. So taking a look at, say, this one right here, which is 103 and 300ths. Expanded form means to write each of the digits multiplied by what it's being multiplied by. So this is 1 times 100. I'm going to put in the 0 times 10 just so that I know that I did them all. If you left out the 0 times 10, it would be okay. We have 3 times 1. We have 0 times 1/10. And then we have 3 times 1/100th. So what does this do for us? Well, one of the things that it does is it reminds us that the values themselves, the 1s and the 3s, don't really mean 1 and 3, right? They mean 1 in the 100th place, or they mean 3 in the 100th place. And so they have a different meaning. The numerical values themselves, locations, matter. And this helps us to remember that they do in fact matter and have value depending on where they are. Now, a visual picture that we're going to be using is called a decimal square grid. And my grids are not going to be great. Yours will be better because you have better control, actually, than I do on my iPad, oddly enough. But what I want you to do is draw a large square. That I can do. And you're going to divide it both lengthwise and widthwise into 10 slots. So you're going to divide it into 10 vertical strips and 10 horizontal strips. And yours will look better than mine in the sense that they'll look more equal. Mine will not look quite equal because I do have some limiting capabilities to drawing this in a way that's reasonable. Okay, that could have gone worse. And then I'll do it horizontally as well. Okay. So as we're thinking about this being our decimal square grid, if I had my blocks with me that I use in number theory, so some of you have seen them before, they kind of look like this, but they're red. Mine are anyway. And they look like they call them a flat. They look like a piece of plastic, and it has 100 little of these little guys, right? 100 little boxes, basically. What we're going to be using this for, again, is to give us a visual picture of what's going on. So I'm going to copy and paste mine to the next page because otherwise I'm not going to have time to draw it in a reasonable way. You're welcome on your next page to simply write see previous page or something like that so you don't have to redraw your picture. But our question on number 4 asks us to draw a decimal square grid for a specific number, namely the number 2400ths. So we're going to draw our grid, and then we're going to shade in exactly 24 of them. Now, while it isn't wrong to shade in a random 24, you're probably going to irritate the grader, and if you do it on a test, you're going to irritate me to do that randomly, okay? So let's not irritate people. Like, that's a good rule of thumb. It's far nicer for everybody if you shade in a whole row and call it 10, right? And another whole row and call it 20, and then 4 more and call it 24. So I have 24 of the little square boxes inside of my large square decimal a decimal square grid shaded in. So this kind of goes with that area diagram that we used back in the fractions sections, right? Same idea. I'd like to make a connection for you between fractions and decimals that you may not be aware of, and it's actually a very interesting connection. Sometimes, fractions turn very nicely into decimals, and sometimes they don't, right? You end up with repeating things or just ugly stuff that happens. This theorem, Theorem 7.1, actually talks about when a fraction is able to be turned into a nice, what's called a terminating decimal. So a rational number, a over b in simplest form, can be written as a terminating decimal if and only if the prime factorization of the denominator contains only 2's and 5's. So there's a couple of conditions here you have to be aware of. First of all, your fraction has to be in simplest form. If you proceed before you do that, you might make a mistake depending on the question you're being asked. Got to be in simplest form. After it's in simplest form, what it says that you would do is to look at the denominator and factor it. And if when you factor it, you get anything that's not a 2 or not a 5 or not a bunch of 2's and 5's, and you can have a bunch of them, that's fine. But if you get a 3, or if you were to get a 7 or an 11, anything that's not a 2 or a 5 as a prime number, it's not going to be a terminating decimal. That's just the way it is. So as we take a look at these examples, the first thing we need to do is to reduce. The second thing we need to do is to factor the denominator. And then on this problem, they're asking us that if indeed it does become a terminating decimal, we're going to find it. Okay? So on 9 and 24, the first thing to ask yourself is it reduced? No. what can I divide both the numerator and the denominator by? 3. So I'm going to start by dividing the top and the bottom by 3. You don't have to write the division by 3, but you're going to divide it by 3 at some level to get 3 over 8. Okay, pretty good so far. How does 8 factor? Like if you were going to do a factor tree, what would you get? Okay, 2 times 4, and then 4 is 2 times 2. So my prime factorization for the number 8 has 2 times 2 times 2. Okay? It is, in fact, only 2's. Now, the directions over here say I'm allowed to have 2's and I'm allowed to have 5's. So I'm good, because I only have 2's. So I don't have to have both. I just have to have one or the other and nothing else. So I have the nothing else. I only have 2's, which means that this will terminate. Now, in a very real sense, that means we have more work to do, as opposed to if it didn't terminate, we'd be done on this problem. So it says what we're going to do next is we're going to actually find the terminating decimal. Now, I am perfectly aware that your calculator will take 3 over 8 or even the 9 over 24, and you can hit a button and it turns into a nice terminating decimal. So if you want to check your work that way, I am all about that. That's great. But you're going to show me the division, right? Just like my 7th graders right now, as they do division with some different things, are still showing the long division that they're doing. You're going to show it to me, okay? So you're going to do, and I would still use the simplified one. There's no reason to use the unsimplified one except that it's going to make your life harder. We don't want to do that. So we're going to use the simplified one. So the 3 will be divided by the 8, and it looks like that. So of course we'd ask ourselves, does 8 go into 3? And of course the answer is no. So we would end up putting a decimal point after our 3 and a 0. How many times does 8 go into 30? 3 times. So the decimal point comes straight up. 3 times 8 is 24. And we subtract, and we get 6. I still have a, 6 is not 0, so I'm not done. If I get a 0 at some point here, I'm done. So I put another 0 in. Now I bring a 0 down, and I've got 60. How many times will 8 go into 60? It's 7. 7 times 8 is 56. I subtract and I get 4. Still not 0, so I put on another 0 and bring it down. I have 40. How many times will the 8 go into 40? 5. And 5 times 8 is 40. So at this point, I subtract and I get 0. So you will always, at some point, subtract and get 0 if you were told that it terminated by your work. Like these have to go hand in hand. Eventually, you're going to get a 0 down here. And once you do, you have found the decimal you were looking for. It's 375 thousandths. That's what the value 3/8 as a fraction represents. How about the second one? What's our first step? Reduce. Always reduce. What do they have in common? 2. So I can divide them both by 2. And that will give you what? 5/12. Then we're going to factor 12. How will 12 factor? 3 and 4, or 2 times 6, either way. If you get the 2 times 6, you need to factor the 6. If we have 3 times 4, we factor the 4. And lo and behold, either direction, we have 3, 2, and 2. That's our prime factorization. So, according to theorem 7.1, does it terminate? No. Why not? Yeah, that 3 will not allow it to, right? So if I look at this one right here, this is going to tell me then that it does not terminate. And if you want to grab your calculator just to confirm it, you can see what will happen. If you divide 5 by 12, you'll get a repeating decimal. I don't know what it is, but just for kicks and giggles, we're going to look at it for the moment. It's 0.41, and then the 6 repeats. So if you were to confirm this in your calculator, you're going to see this, except the 6's just keep going on your calculator screen. That's not terminating, right? Terminating means it stops. This one doesn't stop. So you're welcome to check that as you're working. That's actually good news because it means we don't have to do the division. That's really what it means for this particular point. We're going to talk about repeating decimals in 7.3, but not today. All right, so the next thing we're going to look at is ordering decimals. So ordering or comparing decimals. We're going to line the numbers up by place value. We're going to read from left to right to find the first difference, the place where they're different. And then we're going to compare the different digits. So a lot of the times when they give us the numbers that we're going to compare, they give them to us in like a line format, which is the height of unhelpful, by the way. So when I talk about lining things up, I'm talking about putting them sort of stacked one on top of each other. So much easier to work with. If you keep them in a line, you're going to make a mistake somewhere, and so am I, because you're going to lose track, because there's a lot of decimals going on with this particular problem. So we are going to line them up stacked one on top of each other. So I'm going to leave the first one where it is, and then I'm going to write the numbers underneath it. So I have a 13, and then I have a decimal point, and then 4, 9, 2. And then I have a 13, and a decimal point, 4, 9, 1, 8, 3. I might actually need these to be a little bit bigger, so I think I'll rewrite that first one and increase these. I think I'm just not big enough. And then the last one is 13 and a decimal point, 4, 9, 1, 9, 9. Okay, is that okay so far? You don't have to do what I'm about to do, but if it bothers you that they don't have the same length, you can fix that by putting zeros as placeholders, and I think that's helpful for me personally. So I'm going to put mine in. So there's a 0 here that lines up under the 9 above the 8, and then there's a 0 that lines up after the 9 and after that 0. So now they have the same length, and I think it's a lot easier to see them in the same length. So what we're going to do is we're going to work from left to right, just like we read, and we're going to ignore the places where things are the same, right? So it's all the same in the tens place, and it's all the same in the units place, and it's all the same in the tenths place, and it's all the same in the hundredths place. All of those place values match. We're looking for the first place where they are different, and that's the hundredths place. So in particular, which one is different from the rest? The second one, right? And how is it different? Like, is it different larger or is it different smaller? It's larger. So if we're thinking about ordering these from smallest to largest, right, where 1 is my smallest, just so that we can all make sure we're seeing the right way, and then 4 is my largest, then that second one is my largest. So this one is number 4, if you will. We'll come back to my numbering in a minute, but it's this option number 4. And once I've considered and decided it's option number 4, I'm going to ignore it from the rest of my consideration. So now, as I look at these numbers, I'm ignoring the top, or that middle one right there, but I'm recognizing that the rest of them are all 1s. They all match. So I'm going to the next place. I've got a 9, an 8, and a 9. So which one's different? The 8, right? Different, smaller or different, larger? Yeah, it's smaller, and in fact that makes it the smallest one, right? So this one right here is actually the first one. It is the smallest number that I have. So now the 9s match on the top value and the bottom value. So if we go to the last one that I haven't highlighted, which one's smaller? The top one, because there's a 0 there, right? There's a 0 here compared to the 9 here. So that 0 up there is the smaller one, making it the second smallest, and making the last one the third smallest. So as I'm writing my order, it does say to write it from least to greatest. So I used number 1 to be the least value I have. And so we're going to write 13.49183. You're welcome to put a comma if you'd like. I'm not a huge fan of the commas at this point because they've got decimal points, and I know that sometimes our handwriting is not always the neatest, and points and commas might start to, like morph into the same thing. So I like using a less than sign a little bit better just to make sure that there's some clarity there. The second number I had was the first one listed, 13.4919. The third one, which is the bottom on my list, is 13.49199. And then the fourth one, the largest one, is 13.491. 0.92. And you can order any number of them. This is just 4 of them, but you could have more than this. You could just have 2 of them that you're comparing and putting them in order. The last thing I'd like to sort of draw your attention to is an application of decimals. There's a word that we use in evangelical Christian faith, in churches a lot, and the word is tithe. I mean, the Bible uses the word tithe too, but we preach it in a pretty strong way in evangelical churches. So what does the word tithe mean, and how is it related to decimals? So what does the word tithe mean? To give a portion. Can you be more specific?
A portion of your income.
Okay, of your income. Can anybody else add to that?
To the church.
To the church. It's supposed to be to your local church, actually, yes. There's something else? Anybody know? Okay, so it's not just any portion. It's a specific portion. 10%. Okay, so the tithe is actually a percent, 10%. Or as a fraction, it is 1/10. And as a decimal, what would we represent it as? Yeah, 0.1, right? 1/10 like this. So what this means is that you're giving 1/10. That's the portion specifically. And the Bible uses the phrase of your increase. We use that as to meaning income these days. Of your income. And you guys are right, and it's supposed to be to your local church. So when people say something like, I'm tithing to myself, no, you're not. That's not a tithe, right? That's not what it means. You can say you're keeping your tithe, but that's not tithing to yourself. Income to your local church. So in practice, the 10th is a decimal. I've already written at the top, but I'll write this in words. 0.1. And what we do is we take our income So let's say you get a paycheck and it's for $250. Okay, your income's $250, and we take $250 times 0.1. That's what it really is. You probably don't even think that you're doing it that way, but that's what you're doing. What you probably think is, I'm just moving a decimal, right? And that's how we think of it when we do it. But we are. We're taking the decimal point from right here, and we're moving it 1 to the left. That's the equivalent of multiplying by 0.1, and we would have the value 25, and that would be our tithe, the amount that we're giving to the church. So you're using decimals, I hope anyway, every time that you tithe to your church. All right, so we're going to stop there for today. That puts us still with quite a bit of little time here to finish up your group work. There's only 3 problems. I will restructure groups next time, but I wanted to give one more day for you to work with people you've been working with, and then we'll shuffle things up a little bit.